Okay guys, today we're going to start talking about stoichiometry, but before I even get into what that is, let's look at a problem. Say you graduate from school, you go on to own an ice cream shop. You see coming down the road a class of kindergarten kids, 20 small kids coming into the shop. They each want a sundae. Now, you being the great business person you are, you know each sundae needs 50 mils of chocolate syrup, 2 scoops or about a cup of vanilla ice cream, and 1 cherry. All you have on hand are 600 mils of syrup, 25 cups of ice cream, and 20 cherries. How many sundaes can you make? Now, stay with me on these ratios. You have to have that certain set amount, okay? I want you to think, how is this recipe for a syrup like in a chemical equation, and what type of reaction would it represent? Just think about it, jot it on your notes. Here we go. Okay, so I've set this up for us. We need roughly 50 mils of syrup for every 1 cup of ice cream and every 1 cherry. That's going to give us 1 perfect sundae. But the problem is we have 600 mils of syrup, 25 cups of ice cream, and 20 cherries. How many sundaes can we make for these 20 kids sitting in front of us? Let's see what we can do. So if these are amounts that I have to see kind of how many sundaes could I make with each one. So you see, how many times can I get 50 out of 600? How many times can I get 1 out of 25? 1 out of 20? If I had to multiply this recipe, how many total sundaes could I make with what I have? So let's try to figure that out. So here are each of the multipliers. 50 times 12 is 600. 1 times 25 is 25. 1 times 20 is 20. How many sundaes can I make? Well, that depends on which one are we going to run out of first. So look at that middle. Which one will I run out of first? Yep, you got it. I'm going to run out of the syrup first. With this amount of reactants or ingredients, I'm only going to be able to make 12 perfect sundaes. So 8 of these kids are not going to be really happy at the end of the day. So the way we look at this is I'm able to make 12 total sundaes based off the ingredients we have. So this is what we're going to now. How much do I have versus how much will I be able to make? That's what stoichiometry is all about. Okay, so your little visual there with the 50 mils of syrup and the 1 cup of ice cream should get you to thinking that whatever we're looking at now is all about how much we're putting in and getting out. Well, you're right. Stoichiometry is the branch of chemistry that involves calculating the amount of reactants consumed or products formed in a chemical reaction. So you're on your notes now. You're filling that in. Before we can start figuring out quantities, we got to clear up one thing. Those coefficients that we put out front, you can look at them in 2 ways. You can look at them as a number of particles or a number of moles. So if I look at them as particles, they're telling me how many molecules I have. So look at this example. In the example, I have 2 molecules of diatomic hydrogen reacting with 1 molecule of diatomic oxygen to produce 2 molecules of water. So that tells us what we need. You have the same number of each atom on both sides. That's why we've worked on balancing. Let's keep looking at what this means for us. But we can also use those same numbers out front to tell us a number of moles. 2 moles of hydrogen reacts with 1 mole of oxygen to produce 2 moles of H2O. This is also consistent with the law of conservation of mass. So if you look at the molar masses of these, H2 would be 2 grams here, and O2 would be 32 grams. Well, 2 times 2 over here is 4, plus 32 is going to get us 36 grams. And in the end, water's molar mass is 18 grams times 2 is 36. So we can look at it that way because even if we're saying molecules, that's still going to give us the exact same ratio of atoms or moles. So let's keep on moving. The only part you need to worry about is not confusing moles or molecules with mass. Now, we have those terms. 1 mole is a set number of grams, that molar mass, but the numbers out in front are moles. Remember, your grams depend on your element you're working with, okay? So it's not 2 grams plus 1 gram equals 2 grams. That makes no sense at all. So just don't get those confused. So at this point, we're going to start talking about those coefficients as mole ratios. And we call those conversion factors because they're going to get us from one point to another. So if you look at this formula, you have 2 aluminum oxides forming 4 aluminum metal and 3 oxygen gas. So let's look at this as what a conversion factor is. And you guys have been using these, so just stick with me and you'll understand. So for every 2 moles of Al2O3, I get 4 moles of aluminum. And likewise, for every 4 moles of aluminum, I've used 2 moles of Al2O3. And we can find conversion factors for all of these. So I just want you to sit here and think for 1 second. How many conversion factors could you come up with? Which, yeah, we're looking at them like fractions. How many can you come up with? Just try for a second. So this might be how these types of questions are asked on the EOC. What quantities of nitrogen gas and oxygen gas will react completely to give you 2 moles of dinitrogen pentoxide? Basically, guys, balance the formula. So will it be 4 moles of nitrogen or 2 moles of nitrogen? That's your first question. Which one's going to balance with the right? Well, hopefully you see that it cannot be 4. So I'm going to mark A and B out. Cannot be 4 because then I'm going to have 8 moles of nitrogen on the left versus the 4 on the right. That won't balance correctly. And then how do we get to a balanced 10 atoms of oxygen over on the right? Well, I got to stick a 5 in front. So look back at that. If you're still having trouble with balancing, please take some time to go and study that. Okay, so here we're going to talk about a couple of skills. We're going to talk about make sure you can balance, and then we're going to look again at mole ratios because remember, our coefficients give us a mole ratio. So right now you have this equation. You have N2, which is diatomic nitrogen, plus H2, which is diatomic hydrogen, yields ammonia. Now this is all gaseous, so I need you to go through and balance. Make sure I have the same number of atoms on each side, and pause the video right now. Hopefully you see that there are 3 hydrogens needed for every 2 ammonia, and the nitrogen just has 1, so it's an understood 1. I didn't write it in. Now, we can get 6 different conversion factors, 6 different mole ratios from this, and as you know, a ratio is usually read like a fraction. So I'm going to walk you through the first one, and then you're going to try the other 2. So we're going to compare nitrogen to hydrogen. So for every nitrogen, how many hydrogen do we get? Write that as a fraction. Now hopefully you're seeing that there's a 1 in front of nitrogen, a 3 in front of hydrogen. So for every mole of nitrogen, you get 3 moles of hydrogen. Or if I need to flip it the other way for my picket fence, it's going to be 3 moles of hydrogen for every 1 mole of nitrogen. Now that you know what to do, I want you to try hydrogen with ammonia. How many moles of hydrogen make how many moles of ammonia? Try that, and I'll be right back with you. Pause the video. Okay, so looking at the coefficients, you have a 3 in front of hydrogen and a 2 in front of ammonia. So for every 3 moles of hydrogen, I get 2 moles of ammonia, or if I need to flip it, for every 2 moles of ammonia made, I used 3 moles of hydrogen. So keep that in mind. What's being used to make how much? Alright, last one. Try nitrogen with ammonia. Pause the video, look at coefficients, give me 2 fractions. Okay, so when we're looking at the last one, nitrogen and ammonia, you should have seen that you have, for every 1 mole of nitrogen, you get 2 moles of ammonia, or if I have to flip it, for every 2 moles of ammonia, I used 1 mole of nitrogen. Alright, so hopefully you're starting to see that this is kind of a, how much do I put in to get how much? How much syrup did I need to get how many sundaes? Same concept. Okay. Now what's so important to remember is that these balanced equations give us mole ratios. That helps us figure out the amount of reactants we put in and the products we get out of a certain reaction. So if we're given the moles of one substance, we can use that mole ratio to find the moles of another. Okay, so here's a sample problem of what this really will look like using mole ratios. In spacecrafts, the CO2 exhaled by astronauts can be removed by its reaction with lithium hydroxide, LiOH. It follows this reaction below. Carbon dioxide plus 2 lithium hydroxide gives you lithium carbonate and water. Question: how many moles of lithium hydroxide are required to react with 20 moles CO2? The average amount we exhale each day. So plot out your given and unknown in solution. Okay, if you hadn't already paused to do your given and unknown solution, do it now. Okay, here we see our given is the 20 moles of CO2. The unknown is moles of lithium hydroxide. How do we get there? Well, it should be moles CO2 to, there we go, to moles of LiOH. So there's your given, unknown, and solution. Set up your T-chart. Pause now. See what you can do. So here's our T-chart. We put our given in the upper left corner, 20 moles CO2. Now how many moles of CO2, and finish off the conversion factor, how many moles of CO2 are there for every mole of LiOH? So you just look at your balanced reaction or balanced equation in the problem. What's the coefficient for CO2? Good, there's 1 CO2, so you put a 1 in front of moles of CO2, and then look at LiOH. How many LiOHs are in the equation? Good, there are 2 moles of LiOH. Now, that conversion factor, that 2 moles of LiOH for every 1 mole of CO2, comes from the equation, the balanced equation. Now, all we have to do is cancel units and then solve. So we're going to cancel moles CO2 and multiply across the top, divide whatever is on bottom, see what you get. Yep, 20 times 2 is 40 moles LiOH. Well, that was a good job, so let's move on to the next. Now here's some independent practice for you. How many moles of ammonia are needed to produce 12.4 moles of water in the reaction we see here? Look at your mole ratios. Which one are you going to need? What's your given, unknown, and solution? Fill out your T-chart, and you can check on the next slide. Pause now. Okay, so hopefully you got everything set up. You've got your given, unknown, and solution. Your given is 12.4 moles of water. Unknown is how many moles of NH3 were needed to get that 12.4 moles. So we're going to convert from moles of water to moles of ammonia. Now, set it up with your given on top left. Then at the bottom, how many moles of H2O gives how many moles of NH3? So when you do that, you get 4 moles of NH3 for every 6 moles of water. That comes from the balanced equation. Then when you do the math, you should be getting 8.27 moles of NH3. Alright guys, check yourself, see what you need to work on, and we'll see you next lesson. Okay guys, and your homework for this lesson is set 9-1. You can print it from Edmodo or my website under Chapter 9 Materials. I've posted the answers for 1 and 2, so that'll get you started. I'll take this up at the end of next class.